Okay, so looks like we've got a lot of people signing on, so I guess we'll go ahead and get started. So my name is Clancy Rowley. I'm a professor in MAE, and it's my pleasure to introduce Clara O'Farrell, who's going to give today's talk. So Clara was a student in our own department. So as you all probably know, this seminar series was organized by Yulia Mikhailova and has a number of people who are connected with Princeton in some way, giving talks. And they are working in national labs and for NASA and JPL and places like this. And today's talk is by Clara. Her connection to Princeton is she was a 2008 graduate of our department. Then she went off to, in the MAE department, she went off to graduate school at Caltech, where she worked with John DeBerry on a problem at the intersection of fluid mechanics, vortex rings, and dynamical systems. John DeBerry, her advisor, is also a former graduate of this department, so Clara has several connections back to Princeton. It's a real pleasure to welcome her back to give the seminar. And she now works at JPL, the Jet Propulsion Lab, which you know from the many exciting Mars rovers that they build and all sorts of unmanned robotic things they build to send out into space. She was just saying that tomorrow they're going to launch the big Mars 2020 rover. So tomorrow is the launch, and I guess she's going to tell us about some of her contributions to that. So Clara, it's a pleasure to have you here, and feel free to take it away.
Great, thanks Julia and Clancy. It's great to be back virtually as it may be. Yeah, as Clancy was saying, I graduated from Princeton in 2008. Let me start sharing my screen. And after grad school at Caltech, I didn't move very far because I started at JPL. So yes, this series is about conversations with national labs, and JPL is kind of going to be a unusual member of this particular class. So JPL is a part of NASA. NASA, as you may know, has headquarters in Washington, D.C., and then 10 field centers across the U.S. 9 of those field centers are typical government facilities, staffed by civil servants and contractors. And then one of those facilities is an FFRDC, a federally funded research and development center, kind of like the Princeton Plasma Physics Lab, which Princeton manages for the Department of Energy. JPL is NASA's only FFRDC. We also have 7 facilities operated by the different field centers. And as you can see, we're, NASA spread all throughout the country. This is us, JPL here in California and Pasadena. So the agency has 17,000 civil servants and many more, several times the number of contractors, and an annual budget of around 20 million. Within the NASA family, the National Laboratories, or JPL, is the only FFRDC, and it is managed by Caltech for NASA. So it is both a NASA center and a division of Caltech. So all of us at JPL are Caltech employees. There's about 6,000 of us in a 177-acre facility in the foothills of the San Gabriel Mountains in Pasadena. It's not too shabby. And yeah, we manage an annual budget of around $2.5 million. And then the final piece of this puzzle is Caltech, which I think you might have heard of. Some people, like Clancy, may or may not have gone there. So it's a private research university in about 6 miles from JPL in downtown Pasadena, founded in 1891. Has about 300 faculty. Around a little over 2,000 students and 1,300 postdocs. So there we are. So what do we do? So as Clancy was mentioning, you probably heard about this through our work with planetary exploration, particularly Mars exploration. That is one of the biggest things we do. But essentially, we are a national research facility that carries out robotic space exploration, but also earth science missions. So we implement programs in planetary exploration, earth science. We also do some space-based astronomy and a lot of technology development. So if you look at this is a budget for 2019, you know, Mars exploration is called out as a separate item because we do a lot of that Mars exploration, but, you know, we do even more astronomy and physics, exploration of other parts of the solar system, and we do quite a bit actually of Earth science. Most of our spacecraft that we operate at any given time are usually in orbit around Earth. We also manage the Deep Space Network, which is a worldwide system of antennas. That is what basically every space agency except China uses to communicate with this spacecraft. And we also, you know, most of our work is for NASA. Our prime contract with NASA requires that at least 90% of our work be directly for NASA. But we also apply our capabilities to other areas, so we can partner with industry, with universities, and with other government agencies to do work that is, you know, sort of in sync with our mission for NASA. So we do some of that as well. There are approximately 6,000 of us, as I mentioned. Among the technical staff, we're pretty evenly split between, you know, people with bachelor's degrees, masters, and PhDs. In addition to our full-time technical staff, we usually host around 200 postdocs at any given time. So I actually called out a few of the postdoctoral programs that we have here in case anybody is interested. And we also always host a huge number of interns, particularly in the summer. We're just overrun by interns, but also during the academic year. So we host both graduate and undergraduate students. And that is, you know, those students we host through programs directly with JPL, some through NASA programs, you know, co-op programs with NASA. And then Caltech has a summer undergraduate research fellowship program that provides a whole bunch of our interns. So, and then in terms of the particular technical work that we do, you know, this is a bit of an eye chart. You can't quite read that, but what I was trying to highlight was the fact that we do all sorts of works. You know, what you mostly think about when you think about JPL is probably the stuff that's here and what we call Division 31, the systems engineering and formulation. But we have a whole division for science, and, you know, they do earth science, planetary science, oceanography, you know, yeah, all sorts of things, exoplanet studies. We have a lot of expertise in radar because of our deep space network communication. There's a lot of radar scientists out here. A lot of work on instrument design and electric propulsion, all areas of mission design, from the science aspect of it to the running it, you know, the actual communication through the deep space network, the planning operations, you know, building the spacecraft. We do everything. So there's actually quite a few disciplines that all come together here at JPL, from the proposal stage to the actual operation stage. So there's quite a lot of interesting work going on here at JPL. I actually pulled out this picture while we were talking, because I think this is very interesting. So funnily enough, 3 of us from my class ended up at JPL. We are still there. Strangely enough, the 3 of us happen to be women, and we all used to work together. So I took this picture from class day, but this is Carolyn Brennan, who worked on, she was the contract technical manager for the entry, descent, and landing actuators for the Mars 2020 mission, which is the Perseverance rover that we're launching tomorrow. And that is yours truly. And over here we have Sarah Sherman, who worked on the sample caching system, also for the Perseverance rover. So the 3 of us are, strangely enough, still working together more than after graduation, just a slightly bigger project. Yeah, but what I'm going to talk about today is the project that I've been working on, which is the Mars 2020 mission. Mars 2020 is the name that we know it by, but a few months ago we announced that the will be called Perseverance, winner of a national contest on kids. And we are launching, it looks like tomorrow, which is crazy. I think I'm gonna have to stop my video. Hang on a second, because I have bad internet. There we are. So we are scheduled to launch between tomorrow and August 15th out of Kennedy Space Center in Cape Canaveral, Florida on an Atlas V rocket. We will then begin our 7-month cruise and arrive at Mars nominally on February 18th, 2021 to begin our entry, descent, and landing sequence. So those of you who, I'm trying to do some mental math to figure out, but yeah, most of you probably remember the Curiosity rover landing in 2012. So Mars 2020 is a follow-on mission to the Curiosity rover. So it's very similar to Curiosity, but it carries a different set of instruments. So we will arrive at Mars and start an entry, descent, and landing, or EDL sequence that is very similar to what the Curiosity rover did. So we have a guided entry. So we do have a lift generating vehicle that allows us to steer through the atmosphere to hit our landing target. We will then deploy a 21.5-meter parachute when we are traveling at supersonic speeds. We're going to be traveling around 1.75 times the speed of sound. And then after we have gone into the subsonic regime, we will drop our heat shield, turn on our radar, acquire the ground, and then when we reach the desired altitude, we will separate from our parachute and start a power descent phase. That power descent phase culminates in what we call the sky crane maneuver. So that's what's shown here in this picture. So we have our power descent vehicle with our main landing engines. When we start our power descent phase, the rover is tucked in here under the power descent vehicle. And then when we're 21 meters over the surface of Mars, we start reeling it down until it touches the surface. That's what we call the sky crane maneuver. Some changes that we made from the Curiosity rover is that this time around we have what we call a range trigger. So the entire entry, descent, and landing sequence is autonomous. It takes around 14 minutes from signals to reach to travel from Earth to Mars. So we cannot joystick this. It has to all be autonomous. In the past, all of our triggering events were either timers or velocity triggers. This time around, we are actually triggering the deploy of the parachute based on range. So we are going to be integrating our trajectory throughout the entire entry phase. And then when we're 16 kilometers away from our target, we are going to trigger the parachute deploy. What that allows us to do is to have a much smaller landing ellipse. So, you know, we have a nominal target location, and then there's some dispersion around it where we could actually land given, you know, all the uncertainties in atmosphere, you know, vehicle performance, you know, what kind of drag we get from the parachute, what kind of performance we get from our landing engines. But triggering on range as opposed to velocity or time really allows us to shrink that ellipse. And what that allows us to do is it allows us to target much more challenging landing sites because we need to target somewhere that is safe to land, but we also want to be close to interesting science. So those two interests are kind of competing. And you can imagine that the smaller our ellipse, the easier it is to find a safe landing space that is close to interesting science. Another thing that helps us with the targeting more interesting landing spots is TRN, terrain relative navigation. So this time around, for the first time, we're bringing a camera on board, and we're going to use computer vision to decide where the rover lands. So once we are on the parachute, we're going to turn on our lander vision system, or LVS. It's going to take images and compare them against preloaded maps to determine where it is, and then choose one of many pre-selected safe landing targets and divert to that landing target. So again, this also allows us to choose much more interesting landing sites because it allows us to have areas within our ellipse that are hazardous that we wouldn't want to land in, because our lander vision system can identify those areas and then steer away from them so that we can land safely. In the past, before we had this, we had to make sure we didn't have any of these areas we wouldn't want to land in within our landing ellipse, which meant that you had to land in, flat, featureless spaces, which tend to be a little far away from the interesting science. Once we are safely on the surface, we will begin our prime mission, which is 1.5 Mars years. A Mars year is around 2 Earth years. We have the ability to traverse around 20 kilometers in order to complete our science missions. Our main science mission is to seek signs of past life. So we are, for the first time ever, specifically stating that we are going out there to find signs that there was at one point life on Mars. We are also going to, for the first time, drill into the Martian surface, take samples below the Martian surface, and then cache those samples in special tubes, which a follow-on mission would return back to Earth so we can study them in detail. So that is extremely exciting. The amount of science that we get out of those samples would be amazing. We are also preparing the way for human exploration on Mars. So we have some experiments, we have a weather station on board to characterize the climate on Mars. We have an experiment called MOXIE, which is an in situ resource generation experiment. We're going to dissociate carbon dioxide to generate oxygen, which could be used both for breathing and as propellant for exploration of the planet. So it's a very exciting mission, and I recommend that you follow our launch, hopefully tomorrow. Launch window opens 7:50 Eastern time, 4:50 Pacific, 7:50 a.m., 4:50 a.m. for me. So please follow us. So I think I alluded to this before, but this is what our concept of operation looks like for entry, descent, and landing. Around 10 minutes before we hit the Martian atmosphere, so we hit the atmosphere at an altitude of around 125 kilometers over the surface. So around 10 minutes before, we separate from the cruise stage, and at that point, we are autonomous. First thing we do is we jettison some ballast masses. That shifts our center of mass so that we now have a lifting vehicle. And then we enter the Martian atmosphere. We generate a lot of aeroheating as we hit the Martian atmosphere. So our heat shield protects us from the aeroheating. And as I mentioned, as we travel through the atmosphere, we are performing several bank reversals and steering up and down to try to hit our landing target. Once we are out of the hypersonic regime, we start waiting for our integrated solution to tell us we've hit the right range. And when we do, we deploy our supersonic parachute. At that point, we are traveling at a velocity of around 440 meters per second, and we are around 10 kilometers above the Mars aeroid. Once we have gone below Mach 1, we will drop our heat shield, which just tumbles to the ground. It allows us to turn on 2 instruments. The first is our radar, which acquires the ground and tells us which altitude we are at, and also starts giving us a velocity solution. And then we also turn on our lander vision system, which will take several images and figure out where we are so that it can choose what we do in the next step, which is once we reach our back shell separation conditions, we will first let go of the parachute, free fall for 3 seconds, and then execute a divert maneuver to get away from the parachute. So our lander vision system will pick the target that we will use to the target that we will divert to, essentially. And then once we've executed our divert, we start our final powered descent. So we descend onto an altitude of around 21 meters. Then we start reeling out the rover. That's what we call the sky crane maneuver. Once the rover has touched down, we cut the cables, and then the descent stage flies away and we crash it somewhere far away from the rover so that it can't cause any harm to our main mission. So what I worked on was this phase right here, which is the development of the supersonic parachute for this phase. So and I'm going to talk about the work that we did to design and qualify that supersonic parachute. Those of you who are familiar with the Curiosity rover may have noticed that the parachute looks exactly the same as it did for Curiosity. So, you know, we have a mission that's very similar to Curiosity. Why don't we just use the same parachute? And the motivation for that is something that happened a couple of years after Curiosity. So my first project at JPL was a project called the Low Density Supersonic Decelerators project. And that project was designing next generation aerodynamic decelerators. So we were designing among other things, larger supersonic parachutes so that we could land larger payloads on Mars. So this is footage from 2 flight tests from that program. So the thing you're seeing here, this is called a ballute. Ballute is a portmanteau of balloon and parachute. It is an inflatable aerodynamic decelerator, which is used mostly as a pilot device to deploy parachutes supersonically. So we're going to use this ballute to deploy 30.5-meter parachute. So on the left, you see footage from our first test in 2014. On the right is footage from our second test in 2015. And we have some telemetry here in the background, but I think the point will be quite clear. So we go of the ballute, and it's pulling out the parachute. You can see it coming out. Then it starts to inflate, and that. And more of that. So these 2 failures of the parachutes happened at a Mach number of around 2.5, so it was higher than what we're targeting for Curiosity. And the canopies are larger in their different designs, but the key thing was that we had tested these parachutes subsonically on Earth to much higher loads and not seen any problems. So these results really made us question our understanding of how, you know, parachute loads that we measure subsonically translate to supersonic loads. So it really made us rethink our whole paradigm of how we qualify and test supersonic parachutes for use at Mars. So as a result of this, we went back to the drawing board and we did a couple of things. The first was that we took the parachute that we used for the Curiosity landing and we strengthened it. So we kept the geometry the same, but we used stronger materials. And the second was that we said, all right, subsonic testing is not enough. We need a supersonic test campaign. So we stood up a project called Aspire. So that was the Advanced Supersonic Parachute Inflation Research Experiments project. And the objective of this project was to develop the capability to test supersonic parachutes at Mars-relevant conditions. So that means supersonic speeds and low densities. So to do that, we used a sounding rocket platform. And that sounding rocket platform took us to an altitude of around 40 kilometers, where we can achieve the Mach numbers we need at the dynamic pressures that we need. And it allows us to carry sufficient instrumentation so that we can characterize the environment that we actually deployed the parachute in, characterize the loads the parachute saw, and also characterize the performance of the parachute in this environment. We tested 2 candidate designs for the Mars 2020 mission. The first was just a built-to-print version of the Mars Science Laboratory, that is the Curiosity rover. Again, sorry, that's our official mission name, which we use all the time. So when I talk about MSL, I mean the Curiosity rover. So we used a built-to-print MSL parachute. That parachute design is called a disc gap band, and you will see why in a second. And then the second parachute was a strengthened version of that DGB. So the geometry was identical, we just used stronger materials. Both parachutes had a nominal diameter of 21.5 meters, and the goal was to certify at least one of these to use on Mars 2020. We conducted 3 flight tests. The first one, which we called SRO1, was a test of the built-to-print parachute, and we targeted a load of 35,000 pounds. So that's what Curiosity saw at Mars. And the purpose of this test was to, do a shakeout of the test architecture and ensure that this was the right test. We survived this at Mars, we should be able to survive this and see the same performance here on Earth, or, we haven't designed the test properly. So that took place in October 2017. We then conducted 2 more tests in the next 11 months. Those 2 tests were of the strengthened parachute. The first was an incremental strength test, so we went to 47,000 pounds. And then our final test was targeted 70,000 pounds. So that was our strength qualification test of the new design. So I mentioned the 2 parachutes were called disc gap bands, and the reason we call them disc gap bands of DGBs is because the geometry consists of a flat circular disc, a gap, and then a cylindrical band. Both parachutes I mentioned had identical geometry, and they had a diameter 21.5 meters. But for the strengthened parachute, essentially we used materials that were almost 2 times as strong, and it was about 1.5 times heavier. The main broadcloth of all this parachute is just nylon. It's actually not very different from the nylon in your outdoor gear, but all of the structural elements are Kevlar or Technora, so they're both polyaramid materials. So the test architecture that we chose to carry out this test program was a sounding rocket platform. So we had a 2-stage sounding rocket. The first stage was a Terrier rocket, followed by a black ant. And then our payload here at the top, which was around 7.5 meters tall. This whole thing was rail launched, and we were spin stabilized at 4 hertz. After we separated from the second stage, we had a yo-yo D-spin mechanism right here. Sorry, right before second stage separation. And then we wanted to deploy the parachute. We always want to deploy parachutes at an angle of attack near 0. Parachutes don't tend to deploy well in crosswinds. So we had a cold gas ACS system on board our payload to keep our angle of attack near 0. We also had a GlenMach IMU on board the computer and on board the payload and a flight computer. This allows us to trigger deployment of the parachute based on a target dynamic pressure condition. Our parachute sat here right at the rear end of our experiment, and it was mortar deployed. So what you're looking here, this is a mortar can, this is a gas generator. So when we hit the right deployment conditions, we would trigger the gas generators that would pressurize our mortar, and then our parachute, which was packed in here, would shoot out the back of our experiment. The vast majority of our payload was actually foam, because one of the things we needed to do was recover our experiment from the Atlantic Ocean in order to inspect the parachute and also recover our data. So most of our this payload was actually foam for buoyancy. And then we had a gigantic nose cone ballast here at the front. That was partly for aerodynamic stability during our ascent and unpowered phase. And then we jettisoned that before hitting the ocean to aid in recovery. The whole thing was around 1,200 kilograms with the nose cone, and then went down to around 500 kilograms after we dropped the gigantic piece of aluminum that we had up front. We had quite a bit of instrumentation on our payload. So we had a C-band transponder to allow radar tracking, a GPS that allowed us to integrate our trajectory on board, so the flight computer could trigger at the right conditions. This is our GlenMach. That means a gimbaled LN200 navigator with a miniature airborne computer. So this is our combination of IMU and flight computer. This is our parachute pack, and then around the parachute pack, we had an instrumentation ring. We had load pins where the parachute attached to this instrumentation ring. So the parachute was attached to the payload through 3 bridles here at the instrumentation ring, and we were able to measure the aerodynamic load generated by the parachute at those triple bridles. We also had quite a few cameras on the instrumentation ring. So we had 3 what we call situational awareness cameras. Those are GoPros. 2 of those GoPros can actually transmit video via NTSC during the experiment, so we can see what's going on. And we also had 3 high-speed, high-resolution cameras. They were all synchronized and spread around the ring so that we can do some stereo imaging. In addition, we needed to characterize the atmosphere so we could get an idea of the deployment conditions. So we deployed meteorological balloons carrying radiosondes to characterize the atmosphere during our test. So with all this information, we can reconstruct the loads generated by the parachute, the conditions at parachute deploy, mostly the Mach, the dynamic pressure, and the angle of attack. And then we can also, using our cameras, try to reconstruct the parachute shape and position. So I will show a video which was a summary of our test program, which I think does it much better justice than I could do. Hang on a second.
High above the eastern shore of Virginia, a rocket is hurtling through the atmosphere at nearly twice the speed of sound. Attached, a 3,000-pound to test a parachute for Mars. On board, a computer is calculating the altitude and speed to determine the precise time that it will signal to deploy the parachute. These aren't the first tests of parachutes for Mars. 50 years ago, NASA began lofting parachutes to altitudes and speeds meant to simulate the conditions of Mars entry. Those early tests demonstrated the challenges of inflating lightweight materials in a 1,500-mile-an-hour wind and having them survive well enough to help enable a safe landing on the red planet. Today, as our missions become ever more daring, we need new parachutes capable of surviving those strenuous environments, and we need ways of testing them at loads higher than ever before. To make those tests a reality, engineers at NASA's Jet Propulsion Laboratory worked with NASA's Wallops flight facility to develop a new test technique. The Advanced Supersonic Parachute Inflation Research Experiments, or ASPIRE project, uses a 2-stage Blackbrant 9 sounding rocket to carry its payload to the conditions needed to stress the parachute. The rocket is launched out over the Atlantic Ocean and ascends to altitudes where the atmosphere of Earth mimics the atmosphere near the surface of Mars. The third and final ASPIRE test launched on September 7th. The parachute was deployed at nearly twice the speed of sound. In less than half a second, 200 pounds of nylon, Kevlar, and Technora go from a small drum-sized bag with the density of wood to an inflated parachute with the volume of a large house, generating nearly 70,000 pounds of drag. Here, in slow-motion images, you can see the rapid emergence of the parachute as it begins generating the drag crucial for deceleration at Mars. These images give us amazing insights into the physics and early behaviors of a supersonic parachute inflation. The apparent ease of the unfurling and unfolding in the parachute belies the severity of the extreme environment in which this occurs. Awaiting below were a recovery team who had retrieved both the parachute and the payload and returned them to shore. The parachute was then meticulously rinsed and hung to dry before inspection. Miles and miles of thread and over 3 million stitches are used to hold the parachute together, and we will examine each stitch. After 3 successful tests of ASPIRE, NASA has now tested their new parachute at loads and conditions exceeding any large supersonic parachute before it, and 40% higher than the highest load expected for the Mars 2020 mission. Our parachute is now certified for flight at Mars.
Great. That is what we did 3 times. To give you an idea what our trajectory looks like. So we launched out of Wallops Island in the eastern shore of Virginia. So, you know, here we've got the east coast of the United States. Chesapeake Bay over here. That smudge is Philadelphia. So you guys can, oh, there we are. You can kind of see New Jersey over there. So, yep, we launched our first stage burned out about 6 seconds after launch, and you can see it here falling down to the ocean. Then about 2 minutes afterwards, our second stage burned out, and you can see a photograph here taken from our GoPros of our second stage falling away towards the Earth. We hit apogee at around 50 kilometers, and then we started accelerating and building up dynamic pressure on the way down. When we reached an altitude of around 40 kilometers, we fired the motor and deployed the parachute, and then it took about half an hour to descend down to the ocean for recovery. Depending on what the winds look like, the range was somewhere that we flew was somewhere between 50 and 100 kilometers. Looking at the time, so we these are our target conditions for the 3 flights. So we were targeting a dynamic pressure of around 470 for the first flight, 680 for the second flight, and 950 for the third flight. And we were keeping the Mach number pretty constant at around 1.75 on all flights. This is what we actually achieved in each flight. You can see the first and third were actually very close. On our second flight, we actually had an overperforming second stage. So we overshot our dynamic pressure, and we really overshot our Mach number. This here shows, so this is, we usually look at supersonic parachute performance in dynamic pressure and Mach number space. So the dots here show our historical Mars missions and tests of supersonic parachutes. So for example, these two are the Viking landers in 1974, the Spirit and Opportunity rover are these red dots over here, and then the blue dots are previous tests here on Earth. The green dots are our 3 supersonic tests, so you can see that we really pushed the envelope on dynamic pressure. And then the black ellipse is where we estimate that the Mars 2020 parachute will deploy. So as you can see, we've really over-tested, and we're confident that our parachute is certified for flight at Mars. I am going to, I have a mesmerizing slow motion video of the inflation, which I can show during the Q&A period if we got time. One of the things that was very interesting, so here I am showing time traces of the solid lines are the measured load during inflation. Everything has been non-dimensionalized, so the 3 flights can be shown on the same axis. So first flight, second flight, third flight. So this is the time from line stretch. That's when the canopy has completely come out of the bag and is starting to inflate. So the 3 flights are synchronized. And then the dashed lines are the projected area of the canopy. So you can see that one of the interesting things that we saw was that the load led the projected area. So it looks like we're pressurizing the canopy, and that is leading to an increase in area, as opposed to the other way around, as opposed to, canopy spreading out because of inertia, and then the increase in area leading to increase in force. The inflation time decreased for each flight, and one of the things that we saw was this interesting phenomenon we see, which is that in every flight, we saw that after we reach full inflation, we see a dramatic decrease in load. In some cases, up to 50% decrease in load. But that decrease in load is not accompanied by such a dramatic decrease in area. We see a very moderate decrease in area. So what's happening is that we're overpressurizing the canopy, and this is a supersonic inflation, remember. So we have this normal shock that develops in front of the canopy. So once we overpressurize the canopy, what happens is that we push out that shock, some air, fluid spills out, we depressurize, lose a whole lot of force without necessarily losing a lot of area. We don't see a massive collapse of the canopy. But then after the pressure goes down, the shock moves back in and we stabilize, and we can see the load remains pretty constant. In terms of our aerodynamic models, we usually model the aerodynamic performance of parachutes as a function of Mach number only. So usually we just have a drag coefficient that is a function of Mach number. Parachutes are not very sophisticated. They're pretty blunt instruments. So this, the green line shows what our pre-flight model looked like. Our nominal curve is a solid line, and our upper and lower bounds are the dashed curves. And then this magenta fin line, those were the results that we've seen for the Curiosity landing. So those were reconstruct results. That's the information we had going in. And the three thicker lines are the results from our three flights. In general, our model matched pretty well, you know, in the supersonic regime and then the subsonic regime. One thing that we were not expecting is that all our models usually have a very dramatic dip in the transonic region, because that's where we see a lot of interaction between the wake of the, you know, the vehicle that's in front of the parachute and the shock that's in front of the parachute. So you see a lot of interaction with the wake, and that tends to lead to pretty dramatic decrease in performance of the parachute. And we didn't see that in our flight tests. That may be because we were testing behind a very slender body, but in general, we had very good agreement with our pre-flight models. The three tests were extremely successful. We didn't see any significant damage on the parachutes when we inspected the canopy afterwards. Most of the damage that we saw happened during deployment, when the parachute was coming out of the bag, and maybe we saw friction between the canopy and the bag, or between different areas of the canopy. And it was almost imperceptible, you know, for scale. This is, somebody took a picture of the kind of damage we're looking at and put their hotel key card in the background, so you can see an idea of the kind of damage that we're talking about. But we did learn from these inspections, and we made small modifications to the parachute packing and the rigging in between the flights to try to mitigate some of this damage, and every time we did better. So in conclusion, you know, we successfully tested 2 candidate parachutes for Mars 2020 at Mars-relevant conditions between October 2017 and September 2018. And in fact, our second and first flights were both record breakers. The second flight was the highest load ever survived by a supersonic parachute during inflation. And then about 6 months later, we broke that record again with the third flight. We successfully developed an architecture that we can use to test full-scale supersonic parachutes for future landing missions. So we hope to be doing that again for a follow-on Mars mission. And by the time the third flight was successful, we had certified our parachute for use on the Mars 2020 mission a little under 2 years before launch. So I am going to go for my what's next chart. So as I mentioned early on, the Mars 2020 Perseverance rover, it will be caching samples and storing them on the surface of Mars so that a follow-on mission can return them. So this is the current concept for what a Mars sample return architecture will look like. So this year we will send out the Mars 2020 rover, which will collect samples and cache them on the surface. And then there will be 2 follow-on missions. The first is the Earth return orbiter, which would launch first, and then we would have a sample retrieval lander. So the sample retrieval lander would collect the samples, load them on a small rocket called the Mars Ascent Vehicle, which would place those those samples in an orbiting sample. So this is a cache that would be in orbit around Mars, and then the Earth return orbiter, which launched earlier, would rendezvous with that orbiting sample in orbit around Mars and return them to Earth for additional inspections. So this whole architecture is a collaboration between NASA and ESA, and hopefully soon we will become an official mission and start working towards this. So I think that is all I've got. So I will start my video and open them for questions.
Thank you so much. It's a fantastic talk. So exciting to hear about all these details. And I will certainly watch the launch tomorrow. So I have a question. Do these damages in the parachute, do they most often happen near the stitchers? And if yes, how does the robustness, how does it depend on the number of stitches?
So, so yeah, definitely the seams are one. So the seams are the most vulnerable points of the parachute, and often so it depends on the type of damage. So if you're looking at the kind of damage that usually develops because of stresses, then they usually develop at the seams, so building parachutes is a combination of an art and a science, and the folks who do this are incredible. So there's this whole, I mean, this whole area of what materials do you use. Certain threads work well with nylon, others do not. Then there is the stitching pattern that you use. One of the things we try to do is we try to keep the thread count in our nylon material very high, because that gives us better efficiency at those joints. But then yeah, there's the kind of seam that you use. There's how many times you fold it over before you sew it, and things like that. I've learned a lot about sewing and working with this. The kind of damage that we saw in our test was actually mostly deployment related, so it was friction damage as things were coming out of the package, and that can happen anywhere. And the key with that is making sure that it doesn't propagate, so that if you see, so you don't have any stress concentrations where that is unavoidable almost, spread and then lead to catastrophic failure of the parachute.
Thank you so much. We have some questions. Please enter your questions in the chat box. So Catherine Kokmanin has a question. Would you like to ask it live, Catherine?
Sure, yes, hi. Thank you very much for the great talk. I had two questions, if that's okay. My first one was just regarding international students and what the possibilities were for them at JPL.
Yeah, so we do often have international scholars at JPL. How the availability of opportunities for non-US persons really depends on the area that we're working on. So in the science divisions, we do have quite a few international scholars, because the work that we do in the science division tends to not be expert controlled. On the other hand, in some of the engineering divisions, some of the work that we do is expert controlled, because unfortunately it can also be used to create weapons. The availability of opportunities really depends on what you're working on. Often for international students, the best path forward is a postdoc in the science divisions, and then from there transitioning to full-time. Often by that time, so once you're a green card holder, you are a U.S. person, and then you can work on the same things as a U.S. citizen can. So that's usually the best path forward for international scholars.
Okay, great, thank you. I was also curious regarding the maximum Mach number seen by the rover throughout the entirety of the mission. You had mentioned hypersonic flow at some point. I was just curious to know if you had a number.
Well, so I mean, the thing is, like, when we actually start, it's infinity, right? Because we come out, I mean, we're coming at 7 kilometers per second, and we haven't even, we're not even in the continuum regime. Right. So, it's just undefined. You try to do that number, and it's absolute garbage. So, yeah. But we start really Mach 15 is when we start saying, okay, all right, let's actually try to do something.
Right. Okay, thank you.
Thank you so much. So another question is, what is the path to a staff position at JPL? if you are a recent graduate student, for example, you're recently graduated, so what should you do if you would like to get a position?
Well, it kind of depends on what you're interested in. If you're interested in the science divisions, usually a postdoc is the way to go. And you know, JPL has postdoc programs, NASA has postdoc programs. We also have a visiting postdoc program where if you have funding for somewhere else, say could be Caltech, that's a pretty common thing, a shared appointment between Caltech and JPL. Often for international students, they might be funded through their home country. So for the science divisions, often it starts with a postdoc, and postdoc appointments are usually from 1 year, for 1 year, renewal for up to 3 years, and then from there on. For engineering appointments, you know, just go to JPL jobs. And you know, opportunities are listed there. As I said, you know, our technical staff is, you know, we hire bachelors, we hire masters, we hire PhDs. So, you know, their opportunities are always available. And we have a special a special category for early career hires, which is everyone within 5 years of their last degree, whatever that might be, where, you know, they kind of look for more general resumes as opposed to, you know, particularly defined positions. But, you know, also go on Tiger, is it still called Tiger Tracks? There's quite a few Princeton alums at JPL. You know, I mentioned myself and 2 of my classmates, but Chad Edwards, who was physics, I believe, is pretty high up at JPL. The project manager for the project I mentioned, Tom Randolph, he got his master's in MAE. Actually, he was a classmate of Eddie Tueri's. So yeah, you know, just go on Tiger Tracks, shoot us an email, send us your resume. We will pass it around.
Thank you so much. So another question is, typically, how many different projects would someone work on over the course of 10 years, let's say, at JPL?
It really depends. So, you know, we have these big, so we have some of the projects we work on are like big flagship missions like Mars 2020 rover. We've been working on this for 8 years now. So, you know, presumably, so my classmates who joined right after graduation, they worked on Curiosity, which was, you know, 4 years away from landing at that point. And then they moved on to working on 2020, right? So that's, you know, yeah, graduated 12 years ago and have worked on 2 projects kind of thing. But we also have a lot of smaller technology demonstration projects. We have a lot of, you know, proposals and studies. So it kind of is up to you what you like working on. I know plenty of people who prefer the small projects, and they might be working on 3 or 4 projects at a time that last 1 or 2 years. I personally prefer working on the big missions. So I have worked on 2 projects in my 8 years at JPL. So it depends. There's some freedom depending on what you want to do and what the needs of the lab are at the time.
Thank you. Do you collaborate with other national labs and also with other universities?
Yeah, we collaborate with Sandia a lot, actually, Sandia National Labs. We do have quite a bit. So we have a lot of collaboration with Caltech, obviously for obvious reasons, but we also have a lot of collaboration with other universities. JPL has a lot of internal funding programs. You know, out of the everything that we do here has some amount of overhead, like it would at a university, and that overhead goes to pay for things like some of these research projects. So if anybody is interested in collaborating with someone at JPL, Princeton is actually one of the universities that's on JPL's Strategic University Research Partnership. So if you're interested in working on something like that, you know, you can find a researcher at JPL who's working on this, and you guys can both apply to what we call SERP funding for a proposal. I mean, Jeremy Kasten is often working with us. So, yeah.
Nice, thank you. And what is the main difference between working in national and JPL and universities? What
Well,
is your working day about, for example?
So for me, I've mostly worked on test programs. So some things about it are not particularly different from someone, an experimentalist working on a big experiment, right? I mean, there's the time leading up to it is experiment design, instrument selection, just test matrix design and working through all of that. And then the money funding exercises and asking for money and then asking for money again and all that stuff. And then there is the fun stuff, which is actually running the experiment, which is like going to summer camp. And then afterwards, there's, weeks and months of experiment processing. So that part of it is maybe not that different. What is different for me is, I think, pretty much everything that we work on here is pretty big. So we work in pretty big teams. You don't go to Mars by yourself, which personally I love. It's one of the reasons that I love working at JPL is, the people that we have here are great. And I get to work with them every day because, the people at Caltech, we had at Caltech were awesome too. But if you're a theoretical fluid dynamicist, you might as well be on Mars in some senses. So that's a little different. The other thing that can be a little different too is that so if you're working on a research program or if you're working in the science divisions, the research or the purpose of the research is not particularly different from what it would be at a university. But once you're working on a flight project, the end goal of the research is to get its mission success. So you're looking for good enough and reliable. And once you get to that point, it's pencils down, right? So sometimes you don't get to continue looking into something for your own edification like you would at a university. So sometimes you can miss that, the idea of, diving into something until you know everything about it. That's not the goal for a flight project.
Thank you so much. Clara, you mentioned funding. Where does the funding come from? Do you need to submit some internal proposals or is it external funding?
It depends again on what you're working on. 90% of JPL's funding comes directly from NASA. The other 10% can come from industry, other government agencies, etc. And that usually comes from you apply to external proposal calls. Researchers apply to external proposal calls and get funded. Then for the NASA funding itself, some of the big missions, like for example the Perseverance rover, are directed. So NASA headquarters told JPL do this. Others are competed. So for example, the Discovery class missions, the New Frontiers class missions, those are competed. So a team at JPL, at Langley, at Ames, or whatever, at NASA Center would put together a proposal, and then a certain number of them get awarded. So depending on what you like to work on, if you like to work on flight projects, on really big missions like Perseverance, the funding will come directly from NASA. Medium-sized projects, you might get to work on the proposal team, which is a lot of fun. I worked on a proposal team that didn't get funded, but still it was fun. And then eventually the funding will come from NASA. But then if you like working on like smaller technology demonstration missions and things like that, then you would be applying for internal JPL funding, for NASA funding, maybe through NSF funding. You can still apply as an FFRDC. JPL is eligible to apply for a lot of the same funding sources that you would apply at at Princeton, Caltech, wherever. But yeah, not all of them, but a lot of them.
If something doesn't get funding, how do you usually proceed? Do you continue to apply like next year, or you just give up?
Well, some of these bigger calls only come every few years, right? So if you're working on Discovery or a New Frontiers mission, a lot of the times, you kind of put it away for a few years and then try again. And then maybe you apply for internal funding to keep some of the stuff going. A lot of times you use the feedback that you got from the proposal to try to apply for smaller internal funding to advance that particular area of technology development so you have a better case next time around. So yeah, it depends. I mean, a lot of times if it's something that is and you're passionate about, you keep applying, you knock on doors to find someone who will fund some particular part of it, maybe partner with industry. But sometimes, there's a launch of something big coming up, and if you're in the engineering divisions and not on the science divisions, sometimes you're needed to help on a big project. So you might have to put your research project aside because you need to work operations for Juno or Perseverance. So I personally love JPL. I'm super happy here. But the people who but that's because I really enjoy working on flight projects. I love working on the test programs. That's actually my favorite part of it. And when somebody comes and asks me, would you like to work on this test? I'm like, yes, you had me at test. I don't even care what it's for. So I really like the research part of it too. But I like working on the big flight projects. The folks who really like working on the smaller, more self-directed research projects, they have to make that happen. That's more dependent on you. So if that's what you really want to do, you will have to.
Thank you. Do you hear me, Clara?
Yeah.
Great. Thank you. Is there anything you find difficult at JPL? Something you struggle with?
Well, so I mean, personally, I think it was a great fit for me. Not everyone that I know who came here feels that way. I mentioned particularly people who are more into more fundamental research. Maybe they struggle a little bit with balancing fundamental research with work. But for me, it's been overall a great experience. I mean, some of the red tape that comes with working at a gigantic government agency can be interesting. Some of the frustrations that have to do with funding, particularly as they relate to things like, will we pass a budget or not? It's like all the other NASA centers are shut down because the government is shut down. That kind of stuff can be interesting. But yeah, it's a small price to pay as far as I'm concerned.
How did the current pandemic affect the situation?
NASA in general, we realized that we have some critical missions that need to get off the ground. So it was imperative that we don't lose a lot of our workforce, that a lot of our workforce doesn't go down because they're sick with COVID. So we went on mandatory telework very early, in early March. Obviously, the key personnel who are needed to build and test spacecraft, particularly for the missions that are heading to the launch pad, and the people who are operating spacecraft, operating the deep space network, they were still working. So we went on a skeleton crew with lots of procedures for safety testing, etc. And then everybody else has been working from home. So it's been really interesting to try to build and operate a spacecraft from our living rooms. It's been something very different.
Right, interesting times.
Yeah.
Couple of more questions. What about the diversity in your team? So you showed us you have at least 3 female Princetonians in your team.
Yeah, that's kind of an anomaly. Usually it's around 25%. So I haven't seen the latest statistics. I know the director sent an email that they were going to release the latest diversity and workforce statistics. What I do know is that the percentage of women among the technical staff is around 25 to 30%, depending year to year. There's a lot of variation with disciplines. So some areas of JPL, like the science divisions, chemistry, etc., have a higher percentage of women than others. So yeah, the experience can vary a lot depending on what particular project or area you happen to be working on. I don't know about other underrepresented groups off the top of my head because I haven't seen the latest statistics.
Thank you. And perhaps the last question, what advice would you give to someone who wants to join your team?
So I guess what I was working so
what to start with?
Yeah, be very persistent. So one of the things that I think the reason why they do a good job of actually hiring people who fit in well at JPL is because, you know, it's not just human resources that says, all right, we're hiring this person. The technical staff are responsible for hiring. On the other hand, we would all much rather play with, you know, technical stuff than actually read through resumes. So as a result, you know, the process can be a little slow and frustrating. So be persistent. I drove people nuts. Like I emailed, I called. There is a pretty famous engineer in entry and central landing called Miguel San Martin, who happens to be from my home country. So my mom got me his email address and I emailed him. I was totally shameless. And you should definitely, you should be too.
Thank you. Actually, we have one more question from Dennis Anthony. Would you like to ask it live, Dennis?
Yes, sure. Hey, Clara, great talk, by the way. Just two quick questions. So my first one was, so I know you said JPL hires people that has a bachelor's, master's, PhD, but is there a big difference between like what each can work on there? Like, is a person with a PhD, are they given like a heavier load, or are they kind of focused on something like in particular? Maybe a silly question, but just curious.
No, I think that really depends on the area. So if you look at, you know, some areas like maybe thermal, electric propulsion, stuff like that, and the science areas will tend to have a much higher percentage of PhDs. But in the more general engineering areas, honestly, it's pretty even. You know, I work with people from all, you know, we've had chief engineers of the lab. You know, our current chief engineer of the lab is Rob Manning, who's a, you know, bachelor's from Caltech, but he doesn't have any advanced degrees. Nobody would ever think that they know more than Rob Manning because they have a PhD. You know, it really doesn't. It really doesn't make a difference unless you want to work on something very specific that tends to require an advanced degree, because the particular discipline that you want to work on requires an advanced degree. JPL does have a tuition reimbursement program, so a lot of people who come in with bachelor's do end up getting a master's during a time here at JPL, either at USC and UCLA, or, you know, remotely. Often Michigan and Purdue, I think, are pretty common candidates for that. So if you're, you know, you got a bachelor's and are interested in pursuing a master's at some point, JPL supports.
Thank you so much.
Yeah, no, thank you. And my last one would be what is the diversity like at JPL?
So I think it's one of those things where I don't know the exact numbers. We're working on it, is probably the answer they will give you. I mean, I think, you know, personally, I would like to see a lot, but a lot more, just, you know, opportunities for from folks from underrepresented, traditionally underrepresented groups. I think Caltech and JPL have made that a priority in recent years. They've been partnering with, you know, the National Society of Black Engineers, the Society of Hispanic Professional Engineers, Society of Women Engineers, to try to, do just network more, you know, go to national conferences, make sure we do a better job of recruiting outside of our usual, our usual grounds, so that we can have a more diverse population. Unfortunately, it's one of the things where COVID really doesn't help in that situation, right? There's no conferences, there's no, so, you know, you're trying to reach out in new areas, and COVID doesn't really help, which is a real shame. But they're working on it, and they're trying to being engineers, they're like developing all these metrics to showing improvement from year to year. So I'm hoping that we will see some good results in the next few years.
Thank you.
Thank you so much, Clara. It was really extremely enjoyable conversation, and I liked your fantastic talk a lot.
No, thank you so much for having me. It's great, to reconnect with Princeton during the pandemic, even if it is virtually. So yeah, thank you so much. It was great. It was a lot of fun. Thank you everyone for coming, for the questions, for everything. It was great.
Thanks everyone for participating, and I look forward to launch tomorrow. So I guess many of us will be watching now.
Yeah, you guys don't even have to get up that early. So yeah, watch. Yeah, support us from over there.
Right. Thank you. Have a great day, everyone.
Great. Thank you very much.
Bye-bye.